driven system is lightly damped. The graph, capitalized, right? Shows the variation of the driving frequency of the amplitude of oscillation. So here's our, of course, our resonant frequency like that, right? And what they say is show what this curve would look like if we increased the damping force, right? And one of the things that happens with this is that it actually shifts that peak to the left. It makes it just slightly less, right? The damping goes like a little bit to the left. And we start out the same, right? And then we go up a little bit to the left. And then on the mark scheme, they say the lower peak, right? So, draw that thing. It's a little harder for me to draw, but you can draw a better one, right? Identical behavior to the original curve at the extremes. I agree here. I think these definitely are the same. I think this one is like below that one, unless if we go far enough out, they're the same, right? So they really wanted us to do this. So we better do that, right? And then the peak frequency is shifted to the left. So this thing's shifted to the left, and it's also lower. That's what they're looking for. There were 3 ways to get a mark, but you only could get 2 marks, right? And then it says, a mass on a spring is forced to oscillate by connecting it to a sine wave vibrator. Okay, there's that word again. The graph shows a variation of time t with the resulting displacement y of the mass. A sine vibrator has the same frequency as the natural frequency of the spring mass system. State and explain the displacement of the sine wave vibrator at 8 seconds. Well, where's 8 seconds? 8 seconds is right there. Okay, so this thing is at its peak, right? And this is our mass, right? The mass on the string, right? Okay. Remember that this is the driven mass, and so the mass lags 90 degrees behind the vibrator. Okay. So therefore, the vibrator, well, 90 degrees behind. If this guy's 90 degrees behind, that means the vibrator is already here, right? This is 90 degrees because this would be 2 pi, right, from here to here, right? So this is 360 degrees. That'd be 1/4 of that, or 90 degrees. Okay, so the vibrator is at 0. All right. Which is, by the way, the only answer we could give, because this is the displacement of the spring. We have no idea what the amplitude of the oscillation of the vibrator is, right? It's not necessarily 20 millimeters or whatever that is, right? The vibrator is switched off and the spring continues to oscillate. The Q factor is 25. Calculate the ratio of the energy stored over the power loss for the system, right? So let's find that. Now this formula is for this thing, right? When notice it says power loss on there, so it's energy stored not over energy dissipated, but power loss, right? So we're going to use Q is 2 pi times the frequency, right? Times energy stored over power lost. And they just want us to find this ratio right there. Okay, and that's just simply going to be Q divided by 2 pi frequency naught, right? Okay, so we're going to plug in 25 for our Q, right? That equals 2 pi. And then what is our frequency? That's true. What is that? Our frequency is, in 8 seconds, right? It does 1 cycle, right? So if the period is 8 seconds, then the frequency is 1/8, right? And then that's times the stored, the power lost, right? Okay, so now we're all set, right? We're going to take our calculator and we're going to calculate this thing, right? Which is going to be 25 divided by parentheses 2 pi, and then divided by 1/8, right? And I get 31.8 equals energy stored over power lost. And that's what they want, right? Okay, then they round it to 32. All right, there you go. So this is really, the Q factor is just kind of this arbitrary thing that engineers, it's like a Reynolds number, really, which I don't know if you've gotten to Reynolds numbers or not, right? But it's just an arbitrary thing that they calculate. High Q factors are lightly damped. Low Q factors are kind of like the bounce factor, right? Low Q factors are heavily damped, high are lightly damped.